Thank you very much, Professor Lee, for the kind introduction. And I'm very happy to be here today, and I'm honored to be invited here. My name is Xueyan, and I'm affiliated to Huawei Technology. We are from the Theory Lab. So today I'd like to tell you something about our recent interest in large language models, in particular transformer models. And hopefully we will look at it through the lens of information theory, which is the topic of this workshop. Okay, so first of all, some motivation. So why do we study transformer? This is because, as we can see, large language models have achieved very high capabilities in many downstream tasks. For example, on the left-hand side is research published this year. It shows that GPT-4 has already passed the Turing test, which means that a human cannot distinguish whether he or she is talking to a GPT robot or another human being. So that's very impressive in terms of language models. And also on the right-hand side, it shows that GPT-4 also do very well in many downstream tasks, especially in these tasks related to a lot of knowledges. For example, this research shows that GPT-4 has exceeded the average performance of graduate students in 7 courses in biology, right? So that's very impressive, which means we can potentially use these kind of models to perform downstream tasks. Okay, so from RNN to transformer, these language models have gone through a lot of iterations. First of all, in the 80s, we have these recurrent neural networks, which models the probability distribution in terms of this Markov process. And later, we have this LSTM model, and it is refined to the gated recurrent unit. And finally, we have this transformer model, which perform very well in these kind of large language model tasks. So right now, our focus, most of the focus from industry and academia are on these kind of transformer models. So as a reminder, in case you haven't seen this before, the most important part of the transformer network is arguably this attention mechanism, where we have these 3 matrices we call Curie, key, and values. So they are trainable parameters. So the attention mechanism works like this. So we can take the product of the Curie and key, and then take a softmax between these, and then take the product between the value and the softmax, and it will give us an attention matrix. So in the rest of the talk, we will be focusing on modeling transformer network using something called associative memory that we will see. So this is a paper we recently put on arXiv. So some motivation why we study scaling law is that when we start building a model, there are a few things we want to ask. First of all, of course, we need to know how large the model we want to build. So there is a number of parameter n that we want to know. And the second question is that what data do we have to train the model? So this is another parameter, the number of training samples, D. So we will be looking at the relationship between N, D, and the training laws. So that's the scaling law for language models. And of course, in practice, we have other constraints like hardware and energy, also time constraints. And these are some other issues that in practice we will be considering. On the right-hand side, it's just a comic. So whenever we want to train a neural network, it's just we have some data, and then we give the data to the network, and after some training, it will give you the output you want, right? So this is a very big picture of this scaling law. We want to say that when we have more and more data, so when the number of data are available becomes bigger, and we can train larger and larger models such that their performance is better, given more computational resources. So this is the big picture of the scaling laws. Actually, scaling laws are more universal than just language models. As we can see from 2019, people have been studying scaling laws for other neural network structures like CNN, and also for CLIP model, we have these similar trains. So if you have more parameters, your performance will be better. And another motivation is that we want to make this network training more efficient and more sustainable. Because right now, we can see from this table, training a neural network, training a large language model is very energy consuming, and it incurs a lot of cost. And also, it causes a lot of carbon emission. So we want to make it more efficient. As the CEO of OpenAI has predicted, so in the future, if this scaling law keeps this trend, then it will be the energy that will be the bottleneck of this AI, of large language models and AI advanced development. So this prediction is based on their pioneer work on scaling law, which they first brought up the empirical scaling law for large language models. And we will see from here, this is the scaling law that they developed. It's called chinchilla scaling law, where L is the training loss of the large language model, and N is the number of parameters. D is the number of tokens in the data set. So the empirical chinchilla scaling law, it says that these laws can be written as the summation of the two exponential terms, N to some exponential and D to some exponential. So this is derived from their experiments. So if this chinchilla scaling law holds, in the table below, we can predict that if we want to train larger and larger model, for example, if we want to train 500T model, then the training data we would need will be as large as this, and it will be equivalent to every living human will have to write 4 books for the model to converge, right? So in the future, if this chinchilla scaling law really hold, then the problem will be that we don't have adequate amount of high quality data to train such large models, right? So this is how the empirical scaling laws are derived. So the goal is to feed a parametric form, LND, which can be written as this form. And these A, B, alpha, beta, and E are parameters we want to feed. So what these researchers in OpenAI did is that they train a lot of neural networks, a lot of transformers with different N and D, and then they take the convex Hall of these curves, and then they feed these parameters using this convex Hall. So it gives us the chinchilla scaling law, and it actually performs very well in terms of fitting the curve. But as we can see from this comic, so it is not always true that the extrapolation that you have will be the true prediction for the future, right? So we ask this question, are larger models always better? Because this is what scaling law means. So if you have larger network, you will if it is trained on a larger data set, you will have better performance. But we have already seen some counterexamples. For example, this tiny llama, it has only 1.1 billion parameters. And also we have this mini CPM, which is also very small. And this Phi series developed by Microsoft. These are small language models, but as we can see, they perform almost as good as large models like Llama 2. So it is probably not true that larger language models always perform better than smaller models. Right, so to draw some analogy from biology, we can also look at the human brain. So it is believed that humans have very high intelligence, but we can observe that humans do not always have the largest brain among all the other mammals. For example, we have some dolphins and elephants, animals like these, they may have they may have larger brains, so larger number of parameters, but it is not always true that these animals are more intelligent than human beings, right? So now we will move into to introduce our model. So one observation is that larger models are prone to memorization, as shown in this research. If the number of parameters becomes larger, the fraction of memorization becomes larger as well. So we make the following assumption. Through training, the model will memorize our training samples as some kind of patterns. For example, the sentence structures, things like that could be patterns. And these patterns are denoted by this row, which is vector in Rn. So there are different types of memories in like computer science. We have this kind of KV data set where you can associate the key with a value, which is what you want to retrieve. So given the key, you can find the memory you want to locate. And also in NPU, we have this memory unit, compute unit and memory unit, and then we can iteratively write and read between these two units. So these are types of memories. But in large language models, we use a different type of memory, which is known as associative memory. And this is actually related to the task that the language model is trained on. The task is known as next token prediction. I'm sure some of you may already know this task. So given the first few words were in language models, given the first few words, you want to predict the next token. So this is called next token prediction. It is the same for images. For example, you can tokenize this image so that given a small proportion of this image, the task is to predict the other tokens next to this token. So this is next token prediction, and we can think of it as a kind of memory system where given partial information of this memory, you want to retrieve the whole information, right? So formally speaking, this associative memory is content addressable, which means it is different from the KV dataset or other types of memories in computer science. So it retrieves stored patterns based on part of the content, as we can see from previous examples. But computer memories are based on address, right? So we have this definition. So for every pattern row I, we can find a small ball bi near row I, so that given a query, we can design a dynamic such that a pattern is said to be stored if there exists a fixed point to which the dynamic converge. And the pattern is said to be retrieved if the converged point is epsilon close to the fixed point. So this is kind of like the code book or the code in information theory, where each of the memory vector can be viewed as a code. And you want to put as many codes as possible in this memory space. So we actually study it through the lens of statistical physics, which can be explained using this Boltzmann's law. Suppose we have n particles, x1 through xn. So there will be a probability distribution assigned to this joint distribution, which can be written as exponential e to the power of this minus energy function. And this is normalized by this so-called partition function, which is a constant. For example, in this case, we have for a Boltzmann machine, it has 3 hidden units and 4 visible units. And the Hamiltonian, which is the energy function, can be written as this form. So the energy-based model has been studied by Yang LeCun since 2006. So the principle behind it is that we can potentially capture dependencies through the energy function EXY, and it assigns low energy to points with high probabilities, and it assigns low probability to these high energy points. So given an observation X, our goal will be to minimize this energy function such that we can search for Y that minimize this energy such that it has high probability. As a classical example, in machine learning, we often look at classification problem. So in this case, the data will be in RD space, and we want to classify this data into K labels. So we can take the logit, which is a function from RD to RK, and the softmax function is just like this. And using the Boltzmann's law, we can write it as a joint probability distribution. And to marginalize Y, we will have this log sum exponential, which is the energy function for classification. So this will be used later many times. So it is the energy function for classification, and it's known as the log sum exponential. To model associative memory, there has been work done in the early 80s. It's known as Hopfield network, which associate the input with a stored pattern. So this is a very simple network structure. As we can see, you only have a few nodes and a weight matrix. The update rule is that you take the sign of the weight matrix times the vector, and there's a bias term. And we can prove that this system will eventually converge to this Lyapunov function. So there will be a stable point or a fixed point for this system, and it will be the memory that we want to retrieve. So it is important that Hopfield network is designed, it is not learned. So suppose we know the patterns we want to store, then using this weight matrix, which is the sum of the outer product, we can design an energy function which looks like this, and using this kind of convergence dynamic, we can show that it will converge to one of the patterns we want to retrieve when the system converges. These are just some related work on associative memories. And the first, of course, is Hopfield model, is proposed by Hopfield in the 80s. And then in 2016, a team, they proposed this dense associative memory, where they changed this energy function into this form. where f is a polynomial, it is a arbitrary polynomial. And they show that the capacity can be written at, the capacity reaches polynomial scale. And later in 2017, this team replaced the f function with an exponential function so that the energy becomes the log sum exponential function in like we have seen in the classification problem. So they show that the capacity in this case can achieve exponential capacity. So that's very impressive. And in 2020, this group of team, they developed this modern continuous Hopfield network, which we'll call it MCHN. What they do is that previously it was on binary data, they extended to continuous alphabet, and it still achieves exponential capacity, and it can converge in a single step update. And they also show that this actually looks like the attention mechanism that we mentioned in the transformer network. So to take a closer look, they generalized the classical Hopfield network to continuous valued patterns and achieve exponential storage capacity and one-step convergence. So this is the energy function they proposed. The first part is just a log sum exponential, which is the same as the dense associative memory. And they add these two terms. One is the quadratic term and the other is a normalization term, so that the energy function becomes convex. And they use this concave convex procedure to show that the update rule is actually like the attention mechanism. So this is to relate the previous update rule to the attention mechanism by writing these QKV matrices in this form. We can relate the continuous Hopfield network update to the attention mechanism. So here we introduced a new function that we proposed in this archive paper. So instead of using the dot product in the MCHN network, we propose to use a distance measure D, so that our proposed energy function is actually simpler than the previous energy functions, because we don't need to add some quadratic form to make it convex. We also don't need to add any normalization. It's as simple as a log sum exponential. It's just we replace the dot product with this distance matrix. So we will show that this energy function is actually related to this auxiliary function G, which can be seen as a nearest neighbor search, because if X is a vector in the Euclidean space, it actually searches for the nearest pattern and then returns the distance between this and the pattern. So these are some visualizations. Suppose we have these three two-dimensional patterns. So on the right-hand side is the proposed energy function. We can see that there are 3 points which we want them to converge to. These are the given patterns. And this second surface is the modern Hopfield network. It is the one proposed by the team in 2020. We can see there are also kind of like 3 points, but not as clear as ours. And the left-hand side is the log sum exponential function, which is carried over from the dense associative memory. This is not convex, so this group of people, they add this normalization term to make this convex. So this is what they do, but we show that we don't even need to add this normalization or convex terms. We can already achieve this by simply replacing the dot product with a distance measure. So next, we will show the connection to the nearest neighbor search. So this GX, it functions as a nearest neighbor search. As can be seen on the right-hand side, if a point is in this cell, then it will return the distance between the pattern and the point. So the MCHN energy, it approximates the proposed energy function. This is what we will show. And also the proposed memory is almost equivalent to this auxiliary function. So it is almost like a KNN search when K equals 1. So in principle, in theory, we can replace the attention layer with a search algorithm. This is what we show. So these are the theoretical results. So given a set of patterns, the proposed energy can be bounded by this auxiliary function and a constant. So these are the nearest neighbor search. And the second proposition is to say that the MCHN energy function is very close to the proposed energy function. And the third proposition, it shows that the MCNH function is also close to the auxiliary function, which is the nearest neighbor search. These can be bounded by these parameters. And to visualize the results, we also can plot these energy functions when there are three given patterns, one-dimensional patterns, because we want the curves to be one-dimensional. So this blue line is the proposed energy function, and the orange one is the previously proposed MCNH energy function. These two are bounded, the distance between these two are bounded by some parameters. And also we can see that the red and green are correspond to the nearest neighbor search and with shift by a constant. For the scaling law, we want to study the cross-entropy loss, which is the training loss for next token prediction. It can be written as the summation of the probability of the data times the log of the probability of the model, right? So it's kind of like KL divergence, but without the entropy term. So using the previous model, using the proposed energy function, we show that the cross-entropy loss can be lower bounded by a constant, which is greater than 1, and it can be upper bounded by this log ZT plus 1 over ZT plus log L, right? So there's a lower bound for the cross-entropy loss. This is what we show. We also did some experiments, very small scale experiments. We trained the GPT-2 small model on some data sets. On the Open Web Text 9B data set, we use 100%, 1%, and 0.1% of the data so that it will eventually overtrain. So the result shows that indeed there is a lower bound for the cross-entropy loss, which is greater than 2. Also, we trained the vanilla transformer with 6 layers on this very high quality data set called question formation. So the result shows that the cross-entropy loss is actually lower bounded by 1. And since there are already many literature on large language model training, and these are some commercial large language models that these companies has released the data, released the training details, we can see that the training loss for these models are mostly around 2.2, 2.3. So it shows that the cross-entropy loss should actually be bounded below by some parameter, potentially some 1 point something. So the figure below is a very large scale experiment carried by OpenAI team. So they train a lot of GPT-3 model using different size of parameters and different size of data sets. We can see that the lowest they can get is about 1.75, which is the lowest cross entropy loss. So from here, actually, our result shows that there might be two different roads that we can take from here. One is that we can train bigger and bigger model, and the other one is that we can train smaller models. The first intuition is that because human brain has 10 to about 10 to the 15 synapses, so this could potentially correspond to the number of parameters in a neural network. Right now, we are far below this number, so it might be that bigger models still can benefit us. Another intuition is that if a person reads a book about 80K words every day, and then for 70 years, this person can only consume 2B tokens in total, which is way below the number of training tokens we use nowadays. For example, this NVIDIA introduced this Nemotron 4 model in this June. It has 340B parameters, which is very large in terms of commercial large language models. And the pre-training is carried on over 9 trillion tokens. So this is huge comparing to just 2B tokens. But one good news is that 98% of the training set was synthetic. So they use some technique to synthesize, to generate these training tokens so that potentially we can use a small number of tokens, training tokens, to train a very large network. So this is one way that we can look into. Another one is that we can try to make the network smaller, because right now, comparing to human brain, our hardware is probably not as good. So using smaller network may actually benefit us for some downstream tasks, as we have seen in the tiny llama case. So one way is to simplify the transformer architectures. We can use some simplified blocks or other architecture. Right. The second is to develop some different architectures. Like recently, there's this matrix multiply free architecture, which also reduce the number of parameters largely. So here are some outlooks and challenges that we face in terms of large language models. First, of course, we want to train better models. But I think most importantly, having these pre-trained models, we want to use these models more smartly, more creatively, and more responsibly. Because transformers have some intrinsic constraints that all transformers have. The first one is it has limited context length, as shown in this table. So it means you can only input a certain number of tokens at once to the transformer. Otherwise, it will not process properly the tokens. So most commercial models or most base models are trained on a context window of 4K or 8K. And GPT-4, of course, is not open source. They claim that the context window can be as large as 128K. So I think probably they use some techniques like ours to increase the context window. Right, this is the first problem. And then large language models also face this hallucination problem. where you ask the model a question, it will give you an answer, but you cannot be certain whether this answer is correct or not. It may look correct, but it's actually not correct. So this is the hallucination problem. If we want to use this pre-trained model more responsibly, I think this hallucination should be solved. So to overcome these limitations, one way is to use prompt engineering, because as we can see from this figure, so when we don't give this large language model any prompt, so this is zero shot inference, then the accuracy is actually quite low. It still obeys the scaling law, but the accuracy is not as high. But if you give the model some few short prompts, then the accuracy can be improved greatly. So this is one way we can overcome these limitations. For example, in this paper that is accepted to ACL this year, we developed this semantic compression method to extend the context window of large language models. This is actually inspired by information theory, in particular source coding, where we design a semantic compression module in front of these large language models. So suppose we have a very long sequence of input. We design this semantic compression inspired by source compression in information theory. So we remove the redundancies in the sentences. So the input becomes shorter, but the semantic meaning is preserved, so that if we input this shorter sequence to the large language model, the output will be the same. So this we call it semantic compression. It's like source coding in information theory. So the way we do it is that we design this semantic compression module where you can first divide the input into correlated segments, and then use a pre-trained model to do the compression so that the output will be a shorter sequence with the same semantic meaning. And then we can input this shorter sequence to the large language model. And another problem we are looking into is this long text understanding problem. This is to solve the hallucination problem in when the context length is very long, because often the case when we want to ask the language model some problem related to a very long context, it will fail to give you the correct answer. And if we use some techniques such as RAG, the retrieval augmented generation, so we try to look for the answer of the question from the text and then give that to the model. It also fails because it's likely that there's no direct, the answer is not directly mentioned in the long context. You will need to do some reasoning in order to find the answer. So what we design is a dynamic dynamic way of dividing this question into sub-questions, and each time we use RAG to retrieve the question, the answer of the sub-question, and dynamically update our sub-question. And in the end, it will be able to perform reasoning on this long context and reduce hallucination largely. So this is what we recently put on arXiv as well. So I guess that's all I want to share with us. So thank you very much for your attention, and I'm happy to answer any questions. There's one advertisement. We are actively looking for intern students. So if you are interested, please feel free to contact me. Thank you.
Yeah, thank you, Dr. Liu, for the great talk. So, any question from the audience?
Thank you for the talk. So for the patterns you mentioned, do they refer to like the centroid of like each label in the latent space, or like what do like a pattern refer to here?
This pattern could be very abstract, like structures, like language structures, but in practice, you can view it as some memory that the model learned or it memorized. For example, if you give the model some training samples like this image, it probably will be able to memorize this image so that given part of the image, you will be able to recover the rest.
So it's like each image has a pattern, or like there is a pattern for a group of image.
If we want to make a memorization system, then we will need to memorize all the pictures you give the language model. But right now we are assuming that the language model learns some underlying patterns. So probably there are some underlying low dimensional manifold that the language model learned. So these are the patterns we assume.
Yes, thank you.
Thank you.
Yes. In the first of your talk, you mentioned that ChatGPT can pass the Turing test, and I want to ask, what do you say about this? And this is an open question, and what is the meaning of it? Thank you.
Yeah, thank you very much for the question. So I think I basically just referred to this article this year where they did these experiments comparing human and ChatGPT. I think these are the curves, and human is the blue curve you can see. So ChatGPT 3.5 and 4, I think their accuracy passed 0.5, and this is what they mean by passing the Turing test. But comparing to like real human, I think there's still some gap. So they passed the Turing test. It doesn't mean that they can perform as good as human being.
So ChatGPT-4 is not as good as human in this game.
Yes, I think they probably set a threshold at 0.5.
The second question, you are from Huawei company, right?
Yes.
Do Huawei company now develop some model like this currently?
I cannot speak of for the company, but I know, as far as I know, we have this Pangu model. So this is one model we have. I'm not sure it's open source, but yeah.
Oh, thank you very much. Any other question?
So thank you, Dr. Niu, for your wonderful talk. So it's really inspiring to bridge the large language models and information theory kind of thing together. So in your design, you have the energy function, so which is kind of to make sure that the scaling law works, right, in the in your analysis. So do you have some special requirement or kind of the structure or something for the energy function? So to make sure that maybe for different structures or for different models, maybe for different parameters or something, so the energy function all works. So there's some more relaxed energy function requirement for that.
Thank you very much for the question. It's actually a very important question. So we want to model a transformer. And the one very special thing about transformer is that it uses the attention mechanism. So the energy function is actually trying to model this attention mechanism. It's not modeling the entire transformer network, which includes embedding and like the final layer MLP, right? So it's just it's just attention mechanism. And our energy function is inspired by the 2020 MCNH this energy function. But the problem with their energy function is that they add a lot of redundant term, like this convex term and the normalization term. It looks like they are trying to make this work, but it's not very natural why this works, right? So I think what is most important is this log sum exponential term, which comes from classification. So we are only using this log sum exponential to make this energy function work, and it actually works. Thank you. So because in this paper, they have shown that this energy can be viewed as the update rule for this energy can be viewed as the attention mechanism. So we are saying that since these energy functions and ours are very close, so they may as well be viewed as the transformer network.
Any other question?
Yeah, you just said in some scenario, the large language model not necessarily be better than small language model. I heard a similar comment somewhere else.
Yeah.
So therefore, I want to ask in what kind of scenario where the small language model would prevail?
Yeah, that's a good question. Let me see if this table shows anything. So we can see there are many downstream tasks like coding and math. So if you want to be really good at math or coding, you may probably be able to train a smaller network on some coding data set. So it may outperform your large language model, which is trained not only on coding, but also on other language tasks.
Here, the coding, you mean programming?
Yes, so it's also a language task where you can give like define some function and it will complete the rest of the definition, right?
Okay, thank you.